Hello. So in this video, we'll talk about the mixed strategy and the mixed extension of a strategic game. So now let's first define the mixed strategy. So recall that we use this G, which is a tuple including the n players, okay, and the action profile AI and the utilities, right? So this G is just defined as a strategic game. Okay, so this AI is a vector from A1 to AN. Okay, for each player. Right. So we use this delta AI. Okay, so this delta AI is to denote the set of all distributions, all probability distributions over some set AI. Okay, so namely we just use those this vector including P1, P2 up to Pm in a real of m positive numbers, positive real numbers, and those pi's they sum up to one, right? Because this is a probability. Okay, so then we naturally use this a alpha. The alpha I is a element from this delta AI to denote the mixed strategy for player I. Okay, all right. So if we combine all those alpha i's together, so this alpha vector includes all those alphas, alpha 1, alpha 2, up to alpha n for all those players, right? So which is an element from the product of all those delta AJs. Okay, so for us to more conveniently to study those utilities in the mix extension of a strategic game, then we need to define some sort of the utility functions with those mixed strategies, right? So we define this capital letter UI to be a map from the product of all those delta AJs to a real number, right? So because its utility is just a real number, such that this UI given some alpha is the summation of something. So we sum all those things, which is just the product of those alphas, okay? And the reason is that because those alphas, okay, those things they're independent, okay. So basically, the reason is that each AJ is finite, and given the independence of those randomizations of the probability of the action profile A, right? So, which is just this product of all those alpha J's, okay, and given those AIs, right? So from the perspective of each player I, so the evaluation of this alpha J, okay, for each player, player I's evaluation of alpha J is just the summation over all the A's, okay, and the corresponding the elements here are just the product of all those over all the J's for the alpha J's given those AJ's, right? And multiplied by the UI given A, right? So there has to be a bracket here, right? So we need to multiply all those alpha J's together, given some AI, and for each player J, okay? And after we multiply all those players' possible mixed strategies, given this A, right? Because although this is a product of all the players, but this is still within some certain pure strategy action profile A, right? So after we multiply all those things together, all the probabilities together, then we need to multiply this corresponding utility, this part for the player I, right? Because we are looking for the utility for the player I, okay? And multiply UI given this A. And then finally, after we compute all those expected, all those utilities, then we sum those up. So this is sort of like a probability, but it's multiplied by those many different independent parts of the distinct probabilities for each player, right? Under this case, okay. So that's pretty sufficient for us to understand this definition. Okay, good. So with that, then we can define this mixed extension of a pure of a strategic game, right? Okay, so a mixed extension, okay, of this strategic game and AI UI. Okay, so what is called a mix extension of that? So it's just we replace this this AI with dollar AI. Okay, so that's it. Okay, but notice that this thing here, after we replace the action profile to be the mixed strategies, then this game is completely a different new game, right? So those games, they're different. Okay. All right. So those are just two games. All right. So a mixed strategy Nash equilibrium of a strategic game is a Nash equilibrium of its extension. Okay. So a mixed strategy Nash equilibrium of a strategy game is a Nash equilibrium of its extension. Okay. So namely this mixed strategy Nash equilibrium is just a solution concept for a different kind of game. It's for the of a strategy game is just a Nash equilibrium of its extended game, right? Extension, okay, not extended. It's another thing later. Okay, extension here. So in this new game, the strategies are mixed, right? And then we can consider the mixed strategy Nash equilibrium of this extension of the Nash equilibrium, right? So in this new game, so the strategies are mixed, right? Then we can consider the mixed strategy Nash equilibrium of this extension okay. So remember that the Nash equilibrium's existence had a lot of pretty strict requirements, right? But the existence of the mixed Nash equilibrium is weaker than that, okay, to be satisfied. And we will rigorously prove that and show some of those, show all those requirements later, okay? So before that, let's first take a look at a example, okay? So we just used the matching pennies again. So player 1 could play H or T, so head or tail, and the same for player 2. And their payoffs So for each h is 1 minus 1, here is minus 1, 1, minus 1, 1, here is 1 minus 1, right? Okay, so remember that there was no pure strategy Nash equilibrium, right? Okay, so now we are going to find a mixed strategy Nash equilibrium if there is any. So let's say, okay, alpha 1 for player 1, okay. The probabilities for the mixed strategy for player 1 would be P and 1 minus P, okay. And later we will solve those things. Alpha 2 for player 2 would be just Q and 1 minus Q, okay. So player 1's payoff would be if, okay, if playing H, then player 1 will get Q times 1 plus 1 minus Q times minus 1. H and T for player 2 correspondingly, right? So this would be 2Q minus 1. Okay. Otherwise, player 1 gets Q times minus 1 plus 1 times Q times positive 1. So it will be 1 minus 2Q, right? And we can preliminarily compare those things, right? So if we want to let 2Q minus 1 be greater than 1 minus 2Q, then we can get something like Q is greater than 1 over 2, right? And this is really straightforward. So more rigorously, we can write this best response of player 1 given alpha 2, player 2's mixed strategy. So given that, the player 1's best response, okay, so it would be if Q is greater than a half, so player 1 should just let P to be 1, right? And 1 minus P to be 0, okay? So to play H, right? Because if Q is greater than a half, then playing H can get a higher utility for player 1. Okay, so player 1 should play H all the time, right? Otherwise, if Q is less than half, then this should be 0 and 1, right? But what if Q is exactly in a half? Okay, then in this case, actually any combination, any convex combination should work, right? So P and 1 minus P could be anything between 0 and 1, okay? And maybe you can already see that the mixed strategy Nash exists at some crossing point of those two halves, right? Okay. Yeah, we'll see that later. So if Q is a half, then it means that player 1 could use any probability to play as the mixed strategy, right? Okay, so similarly for player 2, this is very similar, right? So if player 2 is playing H, then it's P times minus 1 plus 1 minus P times 1 is 1 minus 2P. And for T, playing tail is P times 1 plus 1 minus P times minus 1 is 2P minus 1. And if we let 1 minus 2P greater than 2P minus 1, then we can get P less than 1/2, which is just symmetric from the above, right? So correspondingly, B2 given alpha 1 should be, okay, again, 1, 0. If P less than half, if P is exactly a half, then this Q and 1 minus q could be anything, right? If p is greater than a half, then this would be 0, 1. Okay. All right. Okay. And again, so if p is a half, then this will be pretty useful again, right? So because in this case, the player 2 could be playing anything here, right? Okay. So geometrically, we can draw this picture. This is Q, this is P. Okay. So we can just plot those best responses. So here, namely, this should be, okay, if Q is less than a half, then P is 0, right? And let's say this is 1, this is 1 here, this is half, okay. So if Q is greater than a half, then P should be 1. All right. Okay. And similarly, if P is less than a half, then Q is 1. If P is greater than a half, then Q is 0. All right. So what we have found is, so this means that if on those dashed lines, the dashed lines, they simply means that anything on those dashed lines could work, right? Because like from this dashed blue line, so anything here in between works, and the same thing for the red, right? And then obviously we can find this mixed strategy Nash equilibrium right in the middle here at the crossing point, which is just this, right? 0.5 and 0.5. Hey, so a mixed strategy Nash equilibrium is exactly a half P and 1 minus P, Q and 1 minus Q all being a half, right? All right, good. So that's a very good example to demonstrate the basic idea of the mixed strategy Nash equilibrium, right? Okay, now let's have a proposition for the existence of the mixed strategy Nash equilibrium. Okay, and that existence is always true if this game is a finite strategic game or a finite simultaneously move game, right? Okay, so every finite strategic game has a mixed strategy Nash equilibrium, okay, in short. Okay, now let's rigorously prove that. Okay, we just what we are going to do is to show that for every finite strategic game, the requirements are satisfied, right? So then in this case, it has the Nash equilibrium with those mixed strategies. Okay, so and those requirements, just the requirements for the fixed point theorem, right? Remember how we did that in the proof of the existence of pure strategy Nash, right? So suppose this G is a finite strategic game. Okay, again with that tuple, right? So we don't need to bother to write it again. So then for any I player from N, okay, so AI is finite, okay. So we let AI to be A1, A2 up to AN, okay, which is a finite set. Okay, So the mixed strategy of AI is just, again, we use the same notation, P1, P2, PM. Okay, and those P's just sum up to 1, right? Which has probability distributions. Okay, so what we want to do in this proof is to show that this delta AI is non-empty, convex, compact subset of a Euclidean space, right? So we want to show this delta AI is non-empty, okay, convex and compact subset of Euclidean space. All right. So first, to show that this delta AI is closed, okay. So we consider a sequence, right? So to show the closeness, we always use the limit and the sequence, right? Okay, P1K, P2K, dot, PMK, which is a subset of this delta AI. Okay, such that they have a limit if K goes to infinity, right? This goes to some, let's say, P1 star. All right. Okay. Because, okay, this interval 0, 1 is closed, okay, for each element here. So for, let's say, PLK, okay, so this set is within 0 and 1, right? Okay, so the limit 1K goes to infinity, PLK is in 0 and 1, okay? Again, because we have those probabilities sum up to 1, okay? And we have the limit of 1 is still 1, right? Okay, so this is 1, then we just plug into here. So limit of 1 is 1, right? And from here, we can just exchange the order of the limit and this summation, right? So exchange orders, so we can get the summation of the limit to be 1, right? Okay. And this is exactly the PL star, right? So the summation of PL star is 1. So it means that, so because we have the summation of the PL star from 1 to m, right, to be to be 1. So we have P1 star, P2 star, up to PM star. So this has to be within this delta AI, right? Okay, and this is because, okay, why we are saying this? Why this P1 star up to PM star? This guy is within the set of delta AI. So this is because we already show that this star vector is it satisfies the all those properties for the delta AI, right? Okay, so let's just write this formally. So why is that, right? So because the summation of PL star is 1, okay, and the PL star, okay, this is within 0 and 1. So PL star satisfies the definition of the delta AI, right? So what is the definition of delta AI? So we can recall that. So the first is that it's within 0 and 1, and the second is that the summation is 1, right? So those are the two requirements that we need to satisfy to be a typical element of the delta AI, right? Okay, so be more specific, then we can just expand this. So that the AI is something that P1 star, P2 star up to PM star, okay, and this is in 0, 1, and PK star, and this summation is 1, right? Okay, so no matter what we're using for those notations, it is either star or no star or something else, but as long as those things they satisfy those requirements, right? So we can say that those are in the set of AI, right? Because it satisfies this requirement. Then it proves the actually the PK star or the is the limit, right? Is in this delta AI, right? So we can see that this delta AI is closed. So basically, this is the some intuitions in blue here. In blue color is the intuitions for this little proof here, this little part. Okay. All right. Right. So then we can just write it from here. Then so therefore, delta AI is closed. That is to say, because the limit is included, right? So limit is in the set. So because limit is in this set again, right? So this set is closed. Okay. All right. So next we'll show that this set of delta AI is convex, right? So that's another thing we need to show. All right. So to show is convex. Okay. Again, we consider some like two sets, right? Like two different elements in this set AI delta AI. Okay. So let's use P1, P2 up to Pm to be the first point or the first element, and the Q1, Q2 up to Qm to be the second element, and those are both in delta AI. Okay. For any alpha, any number in 0, 1, so we'll use this alpha to make the convex combination of those 2 points. So alpha P, P1, P2 up to Pm plus 1 minus alpha Q1, Q2 up to Qm. Okay. All right, so this is alpha p1 plus 1 minus alpha q1, right? So that's the first, and the second is alpha p2 plus 1 minus alpha q2 dot 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 up to alpha pm plus 1 minus alpha qm, right? And that's it. So we notice that this PL or QL, okay, so they're in 0 and 1 for L from 1 to up to n, okay. So alpha PL is in 0 alpha, so 1 minus alpha QL is in 0 and 1 minus alpha, right? Okay, so alpha PL plus 1 minus alpha QL is in 0 and 1, okay? So the convex combination is in 0, 1, right? Okay. So this convex combination is in 0, 1. That's the meaning of this statement. And what else we can get is the summation over L for alpha PL plus 1 minus alpha QL. So we also need to show that this is 1. And actually it is, because we can just pass the summation into the brackets. So and pull all those alpha minus 1 minus alpha out. So this would be PL plus 1 minus alpha QL, right? And this is again alpha times 1 plus 1 minus alpha times 1 is 1, right? Okay. All right. So that's the first part of this proof, right? And we also need to show the properties for the utility or utility function or the preference relation, right? Okay. So next is the preference relation or the utilities, okay, the properties. So to make it more convenient, so we define some utilities. So we define this preference relation. X is weakly preferred than Y as follows. So for any X and Y in delta, okay, product of AJs, okay, so we say X is weakly preferred and Y if and only if UIX is greater than UIY, okay. Because UI is linear, it must be continuous. So the first requirement is already satisfied, right? So this preference relation is also continuous, okay, for all the I in N, okay. All right. And the next thing is to show the show the quasi concavity, right, of the utility function. Okay, so given is A as a pure strategy profile, okay. So for any let's say Y, okay, in real of M, so we consider some set, okay, where X is in real M, where let's say UIX is greater than UIY, okay. So what we want to show is this set S is convex, right? To show this is convex. And this would be equivalent to show that the utility is quasi-concave, right? UI is quasi-concave. Okay. All right. So how do we do that? So let's define some elements in this set. So let's say a beta and gamma. Those are some elements in S and just some number constant in 0 and 1. Okay. Just show the convexity again, right? So UI of a convex combination of this is lambda beta plus 1 minus lambda gamma. So to expand that, we just substitute all those things into the utility function that we just defined, right? With some probabilities, remember, with the summation first, then the product of all those players, then times the corresponding utility part for the player I in each case, right? So summation over all those pure strategy action profile and times the probability, the product of those independent probabilities. So for all those players J, and what we have is lambda beta J plus 1 minus lambda gamma J. Okay. So this is sort of a notation of the of this mixed strategy, right? Or this probability distribution, and given some AJ, right? And this actually we don't need to write that, but we just denote that okay, this is the pure strategy A for player J, right? And after that, so we have this bracket, very important, this bracket. After that, we time this times the UI of some strategy profile A, right? Okay, so then we can further expand that. So lambda times summation over A action profile, and so what's inside? So it's the product over the J's and beta J with some action AJ and remember those brackets, this is very important, times UI A, right? And plus the other part 1 minus lambda summation A and multiply over all those gammas and UI A. Okay, so what we can see here is just lambda times UI. This is big U, this is small u. Okay, this is big U. UI beta plus 1 minus lambda UI gamma. Okay, and this has to be greater than or equal to lambda UI y plus 1 minus lambda UI y, because each part is correspondingly greater than the other part. So if we sum them up, then this has to be greater than the other one. So this is just UIY, right? Okay. So we showed S is a convex set. So this utility or this preference is quasi-concave. Okay. All right. Then we proved every finite strategic game has a mixed strategy Nash equilibrium, right? Okay, so namely, essentially this finite here, so this finiteness it makes sure that the action space is compact, non-empty Euclidean space, right? Is compact and non-empty, right? So this mixed strategy Nash equilibrium. So this mixed strategy, this mixedness, okay, it makes sure that this action space is convex, right? Okay. So the finiteness makes this the pure strategy gain. Right. So so the finiteness makes sure that this is compact, right, and it's not empty for sure, of course. And this mix here, it makes sure that this action space is convex, right, because it's mixed. Okay. All right. So then this makes that the existence of the mixed strategy Nash equilibrium for the every finite strategic gain, right? So because although the existence of the pure strategy Nash equilibrium needs to satisfy all those requirements, but here since we have the mixed strategy here, so it automatically satisfies some very important properties, and also this finiteness makes sure that this action space is compact and not empty. Right. All right. So and we also know that a pure strategy Nash equilibrium is sort of it could be regarded as a degenerated mixed strategy Nash equilibrium, right? Okay. So okay. So for the last part here, right? So this is pretty long, right? For the quasi-concavity, and in short, okay. So we could, in other words, we can conclude this part in some pretty simple words, and this is because that the expected payoff is linear in the probabilities, right? So each player's payoff function in the mixed extension of a strategic game G will be both quasi-concave in the player's own strategy, and is also continuous, right? So, okay. In short, since expected payoff is linear in the probabilities, so each player's payoff function in the mixed extension of the original game G, this will be both quasi-concave in the player's own strategy, and is continuous, of course. Then this the mixed extension of this mixed extension will satisfy all those requirements that we mentioned previously, right? Okay. All right. So in this video, we covered the mixed strategy and the mixed extension of a strategic game, and we also showed the proof of the existence of that, right? Okay, so later we'll see the this mixed extension or the mixed strategy in Nash equilibrium has a lot of important implications or the applications that we can see in the many real world scenarios. Okay.